So the next view that we're going to consider comes from a philosopher, and that is a man by the name of Karl Popper, Sir Karl Popper, who was living in Austria for a while, worked in an Adlerian psychology lab. Adler was kind of a follower or subsequent to Freud, and he had a lot of similarities to Freud. And Popper began worrying about what made science so special, and how could he tell when people were doing good science and when they were just like making themselves feel good. Um, so he was thinking in particular about some uh, really bad sciences, right? So Freudian psychoanalysis is in the top of his mind professionally, but Nazi science, Nazis had some really fucking shitty science and history. They believed in a fictional race of people called the Nordics or the Aryans were responsible for everything. Um, and you know, yeah, he was particularly motivated at the time because they were very, very vocal and um, outspoken when he was fleeing Austria. Astrology, homeopathy, a bunch of other things were on his mind, a bunch of other issues. And he was worried about how to distinguish the good from the bad. And one thing he began to cotton on to was the fact that when people were admirers of certain views that he found problematic, they seemed to become true believers, right? Like they say this sometimes about conspiracy theories that they are self-sealing, right? That's the same for pseudoscience, right? Um, Everything confirms pseudoscience. If you believe in Marxism or Freudian psychoanalysis, then anything anybody does seems to vindicate the class theory of history or um, the repression or arrested development view of human psychology. Right. So everything confirms your view if you accept it. If you think there's some sort of secret government cabal that's doing things or preventing horrible things from happening, and you only find out about it through 4chan, um, then every bit of evidence will confirm it. If you believe, yeah. So okay. Popper begins to think maybe this is in itself the problem. And I think this is actually probably his biggest contribution. If everything fits, then nothing fits. So here's John Wayne. He's throwing a child in the river. It's relevant. But not just because I like seeing John Wayne throw children in the river. It is very funny to me. But try to think about this from two separate perspectives. One, John Wayne is trying to drown a child who is annoying him in some way. And in another, he's trying to teach him how to swim. Okay? Um, I just love the momentum the child gets. So you can interpret trying to teach the child or trying to drown the child. And if you're a Freudian and I tell you that it's the former or the latter, you will immediately have an explanation, right? He's repressed, or he's figured out a way to address his like childhood trauma, right? Okay. And that's the case for every bit of evidence, every behavior you'll ever see. On the other hand, when you think about the best examples of science, science when it's working at its best, You think about these, right? Boyle's air pump test, Newton's optics, Darwin's origin, the continental drift theory, general theory of relativity, which we talked about in the previous video. So let's go back to that. Einstein makes this wild, wild, wild conjecture in 1915 that space and time are related, that space and gravity and time are related, that acceleration and gravity are the same thing, that when you have a big enough mass object, time and space change. And he says, here's how you would be able to show that I was wrong or right. During a solar eclipse, light would travel near the sun, which is a much more massive object than anything else nearby. And if I'm correct, then the light shouldn't be where it's been. So we've been looking at the stars for millennia, and we have really accurate maps of the stars. Really, 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 really accurate maps. A change in where the stars are would be very, very noticeable, but nobody had thought to look during a solar eclipse with this degree of exactitude until 1919. Actually, people tried immediately after Einstein, but one solar eclipse occurred in 1917, and it was in Russia, and you did not want to be in Russia in 1917. So the next one was in 1919, and Sir Arthur Eddington conducts the experiment and corroborates Einstein. When you think about just how outlandish this had to be, for Einstein to have been wrong would have been nothing, right? Like, the stars are where people have seen them for millennia. Einstein is wrong, reputation is shot, made a prediction, it was wrong. Damn. But because he was right about something so wild, he put himself out there so much, and he was shown to be right, he instantly, overnight, becomes synonymous with genius. His name literally means genius. You call somebody an Einstein, you call him a genius. Popper thought that what happened that made Einstein such good science was that he was taking a risk. The psychoanalysts, the Freudians, don't take risks. Einstein's conjecture was so risky, he could have easily been wrong. In fact, people expected him to be wrong. But because he opened himself up to being wrong, that's what made it science. Science is self-correcting, and the way you self-correct is by eliminating wrong views. So he argues that falsifiability is the criterion for science. Something is falsifiable if you can make some observation that shows it to be wrong. And Popper argued that scientists ought to, and the good science makes as bold of a content possible, as bold of a theory possible, and science proceeds by not rejecting them. So we never get to like show that a theory is correct, but we definitely show that theories are incorrect, and the riskiest theory that has survived the riskiest experiments, that's the one we tentatively accept. For Popper, the biggest value is skepticism. All of those other values that Merton points out aren't as central. What really matters to Popper is that falsifiability value. Merton would probably think that Popper's being overly essentialist. Communities aren't as neat as he thinks, and they are unified in various different ways, in-group and out-group mechanisms. So that's how they disagree. Okay. Lastly, we're going to talk about Thomas Kuhn. He was originally trained as a physicist and then was forced to teach a course in humanities. And he started wrestling with the idea that previous people had been really, really smart. They were just wrong. And he was interested in seeing how these theories changed over time. what changed and what stayed the same. He looked at these historical episodes where we went from one theory, Earth being the center of the universe, or physics, you know, being different on the Earth and the universe and non-Earth, things being designed, that kind of stuff. And we changed within short order to another theory. And Kuhn argues that a history is punctuated by two separate modes: normal science and revolutionary science, theory change. So normal science is what scientists do most of the time. Theory change is what happens periodically, occasionally. Normal science is mostly fact gathering, problem solving, right? Within normal science, there is a way to do science. There is a paradigm, an accepted set of community standards and experiments that people look on as like, this is what makes this particular science. And people keep doing that particular science until somebody comes up with a brand new paradigm. And then maybe they adopt it, or maybe they don't. But that's how it happens. Again and again, paradigms are only replaced by new paradigms. If you stop practicing a paradigm, you stop doing that particular science. So in some areas of study, there's periods before paradigms, and then we develop a way of interpreting and studying the problems. Then maybe there's some anomalies, and they might even cause a crisis. We could resolve them within the paradigm, and a lot of times we do. But sometimes somebody new comes in with a different perspective. Somebody maybe like Thomas Kuhn, and they come up with a new way of structuring the world. And the people that like it follow it. And some older scientists follow it, but most don't. Most just get old and die. And that happens again and again. Science proceeds one funeral at a time. So the same data is interpreted very, very differently from one paradigm to another. Gravity is not the same thing to Newton as it is to Einstein. For Newton, it was a force that was pushing on every object everywhere in the universe all at once and instantly. For Einstein, it is the bending of space and time by acceleration or mass. Same evidence, interpreted differently. You can't see both at the same time. So science shifts under new paradigms, and the world is qualitatively transformed. Okay, let's wrap this up. Kuhn and Popper argued back and forth in the literature about their view. Popper thought that people that were practicing normal science, according to Kuhn, were just doing bad science. Kuhn said, no, actually that is most science. That is what science is. You have an organizing principle. If you stop to overthrow Newtonian physics every time you got a bad result, science would never move forward. Falsifiability happens locally and then broadly, but when it happens over entire theories, it changes the world and it is a huge problem. So here's a famous example. Isaac Newton develops these universal laws of gravitation, and in the 1800s, people deduce that the planets aren't where they should be. In fact, they argue that Neptune is not, that Uranus was not where it was supposed to be. They did this for Uranus when they noticed that Saturn wasn't where it was supposed to be. And they did this for Neptune when Uranus wasn't where it's supposed to be. And in 1930, they did this for Pluto when it wasn't where it was supposed to be. The cool thing about Neptune is like within a year or two, they conjecture where it is, they did the math to figure out where it should be, how big it should be, and then somebody does the observation and they find the planet. But then it turned out that Mercury wasn't where it should be. So they tried the exact same approach. They said, okay, Mercury isn't where Newton's laws say it should be. But we've tried this twice in a row and discovered new planets each time. So there's another planet. Let's call it Vulcan. Literally, it was called Vulcan. That's where Star Trek gets it from. Near Mercury. And then they go and they figure out how big it would be and where it would be, and they look for it and they look for it and they look for it and they can't find it. And they're like, damn. And then they have another idea. They're like, okay, maybe there is, maybe Newton was wrong. Maybe the force of gravity isn't R2, it's R2.0000097. Maybe it wasn't one planet, maybe it was two small planets. You look for those and you can't find those. Maybe it wasn't two small planets, maybe it was many small planets, like a cloud of matter, like a asteroid belt. You look for those, you can't find those. And the quest was only ever abandoned when Einstein had an alternative theory, general relativity, that kind of made the search for Vulcan moot. You shouldn't find Vulcan because Einstein's theories explained exactly why Mercury wasn't where Newton said it should be. So Newton's wrong. He was right for 400 years, or at least was very predictively accurate for 400 years. And then Einstein shows up, has an idea, and is wrong. And so if you think about this, you think about Vulcan. Why is it that the second you can find Vulcan, you don't completely abandon Newtonian mechanics the way Popper suggests you should? It's a falsification. There should be a planet there. There isn't. Falsified. Well, you don't, because it turns out that there's always some secret assumptions you didn't realize you were making. Every single time there's a secret assumption you didn't realize you were making. And there's an infinite number of those, and you can always save the phenomenon from the data. Always, always, always save your theory from whatever you observe. Until somebody comes up with a better theory, and you have to accept that. All right, so that was Kuhn versus Popper, Kuhn versus Merton. I think Kuhn would say something like the Kudos conditions are fine for when Merton said that they applied, but if you look historically, they change over time too, and from place to place, and from field to field. And maybe these are the norms that guide us in choosing paradigms or sabotage us in overcoming them. But really the biggest question is how theories change over time. And they do according to Kuhn's model, he says. Okay, so to wrap it up, sociology of science reveals the norms that bind scientists, or the norms that scientists feel bind them, and the difference between them. Philosophy of science explores what science is and why it is so successful as opposed to other modes of inquiry. History of science explores patterns of science, such as revolutions, and warns us about being too confident. And I think all of these approaches, they seem like they contradict each other, and they do, but I think they all influence each other in an interesting way. If you take them all seriously and on board, you have a much richer understanding of science than if you don't. All right, next lecture, we start getting into the space race. See you next week.